And the wires also need protected when there's a conversion, when there's a change in cross section to get the polyethylene pipe into the fluted section of the deck. You also have potential locations for ingress of moisture, and moisture does get inside these things. All right, let's look at some of the things we've tried on this structure particularly. CABLESCAN's a company, and they have magnetic flux testing. And those of you that have kids in STEM and robotics, promote that. This is a younger crew, at least the crew that came out to do this bridge. They really helped. That basically put this thing like a clamshell around the cable, and then there's motorized vehicles, and they rolled it all the way up the cable and scanned it with magnetic flux testing, and they are able to find cable breaks. Now, fortunately, we did not have any cable breaks, or not cable breaks, wire breaks. Did not have any wire breaks. They're sending a magnetic signal and receiving to see how the volume of the magnetic signal changes. But that's something we've tried as well. Another thing that we've learned since 1985, I'm going to show a video, and I really hope it works because it's worth a watch. If you only get about 20% of the video, I think it'll be just fine. Let's see if it works here. And you notice how those stays are moving. We did not know about this phenomenon in 1985. Now we know about it now. And so here we have this issue happen. This is a bridge in Croatia, so it was not the Frank ASCE bridge or any bridge in Ohio, but still same structure type, same even geometry of the tower and different angles, same general angles. This can be a problem. So the way to solve this issue is to dampen that stay movement, basically putting a hydraulic cylinder on that and to dampen that movement. And that's what we have in this image here. This is in the top of the tower of the Frank ASCE bridge. The best location to put the damper, unfortunately, was way up in the tower at each tower head connection. And notice the cylinder there. There's U-shaped bolts connected to the steel sheath, and then there's the collar on the sheath, on the stay sheath. And then notice that silver piston connecting. That's the dampener mechanism. These things wear out, and these things are proprietary, and so they're difficult for us to pay for. And if your whole structure is, the weakest link is some fluid within a small piston, then you really have to inspect this closely, know what you're doing, and look for any sort of leaking. So this is a damper retrofit. Newer structures we put in, we would put a damper in the build. All right, here's the next structure. That was a 1985 early era. Another thing I should mention about this structure is that we've had issues with creep. We survey the structure, the 1985 one. We survey the structure regularly in order to monitor creep. So there are inches of measurable creep in the structure, and the loads do shift and change, making it more of a challenge. 1990 Veterans Memorial. This is in Steubenville, Ohio, single tower, and I've got another video here that I hope plays. Let me see if this will play. I'm not, I don't work for Majeski Masters, nor do I promote or demote them. I think this video is an excellent video, and they are very good at doing long span inspections, cable stay structures. So this is a video on YouTube using with their permission. Hopefully it'll play.
Here in West Virginia, doing the we're in Steubenville, otherwise known as the Veterans Memorial Bridge. Majeski Masters is here to do the hands-on inspection of the entire length of the bridge. For us, our details primarily include a tower. We're here in West Virginia doing the we're in Steubenville, otherwise known as the Veterans Memorial Bridge. Majeski Masters is here to do the hands-on inspection of the entire length of the bridge. For us, our details primarily include a tower from roadway up a little over 300, 310, 320 foot top tower. down to roadway. We got about longest cable, the rappel would be about a little over 800 feet, 805, 810 feet. We have one crew doing the underbridge inspection vehicles. So they're doing floor system and undersided deck, getting a real detailed look at that portion of the structure. That's what we call our more standard access. And then to get the length, hands-on of the full length of these cables, we use our technical and rope access. A detailed program where we use a two-rope system, primaries and backups. The nice thing is when you use a two-rope system like this, you're pre-rigged for rescue. So it helps us in a lot of aspects. It gives us good control as we go down the cables. We can either go 3 feet, 6 feet, whatever we want to go, and stop, lock off, get a real good look, spin around the cable, look at both sides, underside, top. So it's a real nice hands-on view of the whole thing. For the various locations down the cable, we use laser range finders to shoot back to tower, give us an X coordinate down to the deck, give us the Y coordinate. So we know what cable we're on. I know the X and Y coordinates. So any defects I find can be refound by someone else very easily. This one happens to have multiple lanes, 3 lanes each direction. So shutting down one lane is not that big a deal. The traffic load's low enough. Primary goal here is the safety of the public and the safety of the good hands-on condition inspection of the structure, which ultimately is for the safety of the public. There really is no conventional method. There are multiple ways to do these kind of cable inspections. You can use man lifts, which go, I mean, the standard high man lift's 158 foot. There's a couple that are taller than that, 200, 220 or something. Then you can get to the more exotic where you get a 300-foot crane and you have a basket. Problem with those are they move around a lot. They have very little maneuverability. They have very wide bases, so you're taking multiple lanes, maybe even closing 3 lanes of traffic. Depending on the size of the crane, you may have to shut down the entire bridge. And then with a crane, the basket's gonna be banging into cables and doing damage. Nice thing about the rope access is we can get down to the cables. Our rollers have bearings on them, so wheels spin nice and freely. We don't leave any marks on the cables. We can do that full length, and we can do it far more efficiently and quicker than say you could do with, if you want to call it, the conventional equipment. We've got some marvelous structures across this country, and maintain them is required throughout the life of that structure. If you maintain a structure, you can extend the life of it significantly. Those who don't maintain it, problems arise very quickly. If you take care of the little problems now, they don't become big problems later. Ultimately, as a bridge inspector, our primary client isn't the one that pays it, it's the traveling public. Those guys are the ones that we care about the most. That's why we do what we do. There's a lot of responsibility with that, but in the same line, it's you know, we like what we do. We consider ourselves very thorough on our structures, and that's one of the things that drives us to be thorough on our structures. I've seen bridge owners who do the little things, and they've got 125-year-old bridges with almost no issues on them because they take care of the little things all the way along. They've got maintenance crews that work on these structures on a regular basis. They know their structures. They have a passion for their structures. Those are the kind of clients I like, because one of the things Majeski and Master is we have a passion for bridges, and we have a client who has a passion for their bridges. It's a good fit.
All right, hopefully that came through. Here's an image of, this is courtesy of BNN. This is an image of the U.S. grant structure repelling the cables, rolling the cables. And as we zoom in a little bit, notice this inspector has to maneuver around the collar of the wind tie. These wind ties are a good place to inspect for, make sure they're securely fastened, there's no movement or abrasion. But technically, as a climber, getting around this wind tie is a challenge. As you might imagine, it's pretty daunting to roll these cables. We don't require it. We do require an in-depth inspection, and there are alternatives to rolling, but it is a great way to get an arm's length hands-on inspection that stays. In 2000, Kentucky built the William Harsha Bridge. It's on the Ohio border. This is the biggest main span in our or around our state. The floor beams are fracture critical, and here's some photos. This is a fort, 2-lane, real wide shoulder, and some of the design features. Notice the tie down is completely steel and exposed and painted. And notice on the right-hand photo, on the bottom right-hand photo, we have some pistons. We have some hydraulic mechanisms. And you can't just inspect these like a normal structural inspection. Notice this little puddle down here. Is this puddle hydraulic fluid? Is it just rainwater? Is it a pigeon's last resting place? We don't know without a further inspection. So all those locations need to be looked at. Another design feature on this structure is that the anchorage at the deck goes through the deck. So holes in the deck were made, and the Dewey deck bars are rigidly connected to each side of the web of the beam, the edge girder there. So it's a very interesting design feature. 2001, this is the first cable stay structure built solely in the border, the boundary of Ohio, and it was built by Franklin County engineer. This is in Franklin County on Beach Road on the far northwest corner of the county, and these stays are exposed Dewey deck bars. And there's tie downs, there's link tie downs in the back span full of grease. And this was the precursor to our Lane Avenue Bridge. So if you're familiar with Ohio State campus, this is one of the marquee landmarks on Ohio State campus over the Olentangy River and over the bike trail. And this is a cable stay structure as you're walking into the shot or walking into campus. 2006, we built the U.S. Grant. Notice that there is one tower. There's two towers, but there's one column in each tower. And the stays don't just go down in the X and Y axis, they go down in the Z axis too. So that's another geometric feature you have to figure out when you're trying to load rate, when you're trying to design these things, to figure out what's happening in the load. We'll come back to this one. We'll also come back to Veterans Glass City Skyway. We built this in 2007. Beautiful photo. Notice the structure that's underneath, under here. This is the Craig Memorial, and here's the lift span. This, interestingly, was the last lift span on the interstate. So you can imagine driving 80 miles an hour, some of you, and having to stop to wait for a pleasure cruise to go through the interstate. So we had to build this structure up and over barge traffic. 2008, Bridge of Honor. We built this, designed it, DOT did, or we paid for it at least, and we gave it to West Virginia. So that's completely theirs now. Notice the different geometry of the towers. Very interesting how these are built differently. In 2016, most recent cable stay is the Ironton Russell structure down over the Ohio River. And notice we have the heart shape, and you can see during construction as how we build these. We built them from the back spans, tie down the back spans, and we have temporary supports. And then we have to leave this whole lane open for traffic, barge traffic, commercial traffic, Coast Guard. And we inch out and cantilever these deck pieces out. This is a good way to see that this deck is in compression longitudinally. This deck is meeting with this deck, and it's in compression longitudinally. It's also compression horizontally or transverse to traffic. So the whole deck acts as a strut. Protecting the deck on cable stay structures is very, very important. The way we protect the deck is we replace the overlay more often. We replace the overlay 10 to 15 years. We've done the overlays on 2 of our cable stays already. We're doing the hydro demo on Veterans Glass City Skyway right now because we do not want to have to replace the deck. That is a very complicated, expensive, and demanding replacement when we could have just done preventative maintenance throughout the years. Also, we seal them with HMWM or gravity-fed resin regularly as well. So that is 2016 Ironton Russell. We'll come back to that. Here's a cool video of our drone footage. In my section, I have 2 pilots. That's the snooper truck, and notice we have to close down the entire bridge to do a snooper inspection. So this structure gets closed 3 days every year just to inspect it. So it was narrow, it was a budgetary decision, and that's kind of where we are. It's cool to see the barge in the shot and a good look at the structure. Notice some of the deck anchorage down here, the deck anchorage, as the bell housing goes into the deck. There's extra layers of protection to keep moisture from getting inside the structural members. And if we go to the next, that was a flyby of all of our cable stays. 9 of them. Now, general challenges, I've mentioned some of them. Access is a challenge. Like if you find a problem, getting to the location to fix the problem is a challenge. Inspecting is a challenge. Nothing's impossible. It's just a challenge, getting places. The primary members are covered. That's this inset, the photo down at the bottom. The primary members are those wires, and they are doing lots of heavy lifting, and we protect them because they matter. But inspection is quite a different story. We have to look at context clues, find out if there's cracking around them or if there's separation. We require more rigorous inspection and preventative maintenance on cable stays because it just makes sense. It's less expensive and wise with the public investment to do routine, regular preventative maintenance on keeping the drainage out, more rigorous inspections. And another challenge is this sharing and training idea. There's not too many people that own and operate cable stay structures, and sharing with other states and other consultants, sharing with the last inspection team, that's a bit of a challenge. So the communication piece. Construction is always demanding. It's kind of like whenever I do a home project around the house, I have to remind myself it's going to cost 3 times as much as I think it will. It's going to take me 3 times more time, and I'm going to have to make 3 more trips to the hardware store. So it's kind of like construction. It takes much longer than the estimate. There's flooding, there's other things that come up that people have not considered. Replacement of the deck, you want to avoid that at all costs if you can with preventative maintenance items. Replacing a stay is a bit of a challenge. I've heard it was done on the Luling Bridge in Louisiana. I think the Luling did replace the stay. Some of you might have inside knowledge on that. And then protecting against corrosion and protecting against vandals. So people see a door in a tower, they want to bust it open and explore, climb around, and keeping those doors secure is a challenge. So another challenge is this guy. This is a bridge that collapsed. It's a cable stay structure. Notice the stays, there's a lot fewer stays. There's only 2 covering the one end there. And the stays are pre-stressed concrete tendons. This bridge collapsed in 2018, and it tragically killed 43 people and left 600 people homeless. So these structures, just because they're a marquee landmark, rise above the whole, river valley, they are susceptible to Mother Nature and gravity and live loads, and so this is worth noting that there was a major one in the world collapse. So now moving into the case study. So these are 3 structures I want to talk about. I'll talk about the Ironton Russell, and I believe I'll talk about the Veterans Glass City Skyway and US Grand. Those are the 3 that I'm aware of. So we do in-depth every 5 years on Ironton Russell. That's what we say, at least. We actually do an in-depth every year. We take care of this structure. We take care of all of our cable stays. We say we do a routine, but as I said earlier, we shut down the bridge for 3 days every year, inspect the underside. We started implementing drone inspections into the cable stays because it's easier, simpler, and we have pilots that work for ODOT that are bridge inspectors. Very, very handy. Here's a ballast end for unbalanced. This is in the approach span, actually. This is not in the cable stay, but that is on the structure. So a major problem we had with construction led to some delay claims. The top of these towers, there is a lot of force going in there. You can't just have normally reinforced concrete at the tower. You have to have steel and covered up to make it look like there's concrete, or heavy pre-stressing. And so this structure, and we've done it every single way. So this structure, we had a steel box. You can see it on the top of the tower there, and laying in the shop here. We decided to galvanize this. Galvanizing, a good way to protect things. And when you dip something that is different thicknesses and huge and has different geometries, you're going to get that differential temperature dissipation, and it led to cracking, warping. You can see the warping in the bottom picture and the picture on the right, and this led to major months and months of delay claims. And who hasn't been a part of a major structure where there's lots of different players involved, and this communication, this round-robin communication issue happens, and he said, she said, where the galvanizer was talking to ODOT, and the contractor was talking, we're skipping people in the chain of command. And this was the major finding that we had when building this. So communication, it all came down to communication and how we did or did not do a good job with that. It led to close to a year of delay claims. All right, here's our Untitled Bridge. It's 2019 drone footage, and I'm using this footage as a control just to show you what it should look like. That access hatch, that square access hatch is a lid. The inspector will come out of there, or the person, the electrician that needs to come and change that light bulb for the aerial light. That aerial lighting is so planes know where the top of the tower is. All right, so you got that. That's one tower. Let's go to the next tower. Do you notice a difference? Look on the right-hand corner. There's a bit of an issue with the concrete. We could not have seen this spall without a drone. The angle of which, if you come out of that tower from the access hatch, and if you sight from the bottom, you could not have seen this spall. So the drone saved the day. And we're noticing we're having little success stories with drones. So every month there's a new success story with the drone. It's been a helpful tool in the toolbox for some of our inspectors. And so now fixing that's going to be a problem. The issue here, there is temporary works, bare steel, temporary works for railing and for an elevator for people to epoxy the tower. Once the temporary works were taken down, that face where the steel was, that steel was just cut off and epoxied over. So it was an issue. We're looking at updating our standard to apply to temporary works as well, make sure those are epoxy coated or protected in some way. All right, here's the image looking up from the deck. There's no way you could have seen that spall. Don't know where the spalled concrete went to. It did not, from our knowledge, go into a windshield, fortunately. We think it just kind of slid down into the Ohio River. Here, the photo on the right is a picture of the bell housing, and this is an upgrade. There are what look like circular disc brake pads right in here, and that horizontal friction dampens the movement. And maintenance on these is very easy. Taking the collar off and replacing the brake pad. It's actually easier than replacing a brake pad on that stay there. So that's a good advancement that we've had in the industry. A surprising thing that we found on this structure, much like you'll have that wind, rain oscillation on the stays, well, if you put a real thin bar on the top of the railing out in those elements, we had fatigue cracks that led to fractures. And here's a video you can see in a light rain, heavy wind, we've got fatigue cracking happening on the back end of the supports of the barrier. So I think inspecting a bridge, the best time to inspect a bridge is in the rain. You get to see things that you wouldn't otherwise see. So that was one of our findings. We've since fixed that. Case study 2, Veterans Glass City Skyway. I'm just going to show you some of the pretty pictures in here and skip to the important issues. Drone footage is not also useful in inspecting the stays, but it also offers some really nice marketing videos. Here's some inspectors coming out of the tower and getting ready to rappel down the tower, and inspecting the tower where the sheaths go into the tower and the surrounding connections of the sheaths is very, very important. So this is something we do every 5 to 7 years. Those stay cables are stainless steel. And hey, the drone pilot just, they're people too. They get a little distracted. This drone pilot was a boat guy. Notice the K-stables go down the center line of the bridge, and all that bracing, there needs to be a lot of lateral bracing underneath. Here's the inspectors going down the stay, inspecting that collar connection. And again, we have the redundant wheel rolling contraption. And those stay cables are huge. Look how big they are, much bigger than the other stay cables we have. Stainless steel is probably a bad idea to have in Toledo. When you have stay cables 350 feet above interstate traffic in the winter, there could be problems. And spoiler alert, we'll get to that. Here's a shameless marketing photo. We did precast post-tensioning box sections that we launched into place. You can see one on the left and the right being launched. And in between the boxes, we have the Delta frames post-tension delta frames. Here's a look at the blister from the top and from the underside, the cool looking skeleton type structure where the underside of the blisters. This structure is unique because the stays are not anchored in the deck. Take that back. The stays are not anchored in the tower. That's it. They're only anchored in the deck. So it's saddled through the tower. I'll get to some pictures there. Here we are in 2020. The dampers are corroded. So it's good that we have different designs of dampers. Stuff breaks, stuff corrodes. Keeping that stuff protected and doing good preventative maintenance, it goes a long way. Stay connection to the pylon at construction, this sheath slid down. You can see, if you look here, there's a gap between this collar embedded in the tower and this one, the intermediate collar. So we welded these tabs on and we inspect that every 5 to 7 years, hands-on. Here's the saddles, and each braided wire goes through its own dedicated sheath. And that's the challenge. These are epoxy coated and they go all the way through. And there's your stainless steel separator plate and your stainless steel sheathing, stainless steel tubes. It's a real complicated, only one in the country that I know of that is saddled like this. Now, why don't you do stainless steel 350 feet above traffic? Well, you have falling ice. You have just the right temperature, just the right rain and sleet, just the right, it kind of falls off in big icicles and big circular right through windshields. So this is something we have to close. Veterans Glass City Skyway, that Interstate 280, we have to detour people if there's just the right temperature, just the right mix of snow and sleet. One of my few claims to fame is the AASHTO LRFD bridge design specifications from 2012. Now this has since been replaced, but this photo, see if you can find the photo that is of the Veterans Glass City Skyway. I'll give you a hint. There it is. That's not me, but I did take the photo. And here's a image from another angle of what's happening, different inspectors. This is Mike Schachterly. This is a bridge inspector in District 2, and this was his first rappel. I don't think it was his first rappel ever, but it was pretty darn close. And we made sure he was tied off, and I belayed him, and he rappelled on his own. It was a redundant system. But we're famous now. All right, so here is drone footage of that stay connection, and in my opinion, this drone footage is a very good, handy, intermediate way to inspect these tabs. Now, we can't see if there's any small indications of cracks, but it is a very good confidence builder when we're inspecting structures. As I mentioned, the deck, we don't want to be replacing decks. They act as, they're very, we don't want to replace the whole deck. This is not a standard structure. So we do a lot of overlays. This is our Veterans Glass City Skyway. We're overlaying, we're hydro-demoing right now. And lo and behold, the post-tensioning in the top of the box, the post-tensioning, which is this white sheath that we expose through high-pressure water, it should not be that shallow. It floated to the top in the precast yard, and now here we are having to deal with this. We exposed a lot of post-tensioning. This is the only bridge that I know of that the overlay, the riding surface is integral with the box, and it was all cast together and put in. We would require an overlay be placed after construction and before live traffic to avoid the situations we've had on this structure. So that's an issue, that preventative issue. Also, technical advisory for grout. I won't bore you with that. Here's some cool technology, electrical capacitance volume tomography that we've tried. We didn't use full scale. We tried just out of curiosity, and it seems to work. And for some reason, truckers, when they're burning, they like to park, they're kind of glory hogs. They like to park right in the middle next to the pylon and just let it burn. Makes for very dramatic photos. That's flames shooting down the drainage pipe, down the scupper. All right, last case study, U.S. grant. We've learned a lot on this structure. Here is precast deck panels and floor system. Notice the tower is anchored in different angles, makes for a very complicated load rating. And the deck anchorage is anchored just on one side of this unpainted weathering steel beam. Unpainted weathering steel probably wasn't the best protective measure on the outside there, but it's what we're living with. And if we go to the stays, this is not an uncommon issue that we've seen. This is just a simple fix by releasing and retensioning the wind ties. This is a wind tie. So we've since done that and anchored all the wind ties down to the deck. Standard inspection with the snooper truck. And here's the snooper truck. Takes a very skilled operator to weave through the stays. And another option for inspection is this monstrous man lift. I personally have gotten stuck at the top of this man lift on this bridge for more than an hour. It's not pleasant. So we do not do the man lift anymore. We'd rather rappel. We think that's a little safer. So here's rappelling. And we do confined space. And in order to verify and justify load permits, we've done pull-off tests, and we've done what's called vibration tests, where you simply shake and disturb the stay. First, you take off the wind ties, take off the dampers, and you shake it violently, and you measure the frequency, and you can back calculate the frequency into the tension in the cable. Now it's off. It was off 28% from the pull-off test, but it's something that you can use very simply and easily relative to the same stay, relative to other stays in future inspections. You can develop a system like that. So skip the chloride ion tests. I mentioned that some of the uplift issues, we had some significant uplift issues. Here's the snooper truck inspecting right in this area. This is where we have the tie down on this structure. And as you're inspecting, notice the issues. This is not normally reinforced, something that can be avoided. This is pull-off issues where it's self-desiccating, it's breaking itself apart. And look at the back end, we've got some uplift issues. So this made us nervous early in its life. I think within 3 years, we started seeing major structural cracks in the back end. This is during construction. Here's the post-tension Dewey dags holding down, tying down that uplift. And we just got tired of not knowing what was happening. So much so that we just built a whole supplemental tie-down system. Here's rock-socketed floor beam, and then we put 2 floor beams up inside the bay, and then just tied them all together. So we built a supplemental tie-down system. That tie-down's been a bit of an issue. During the design process and during the scoping of building complex cable stay structures, or any complex structure for that matter, installing structural health monitoring systems that are robust at the design stage is necessary. Having structural health monitoring, this is the one place where I'll agree that structural health monitoring should be used on big structures where we can't really see what's happening. There is an ASCE report 848 that might be helpful and beneficial if you're going to get into this type of work. And lastly, I have 5 questions for you. Hopefully I haven't gone over my time. And question 1, hopefully you're paying attention because I'm watching you. I'm seeing if you are paying attention, see if you can get this question right. Question 1, why is the top wearing surface of the deck more significant in a cable stay bridge versus a more conventional steel beam structure? Give you 2 seconds to answer, and then I will give you the answer. The deck acts as a structural element, and replacing it would require significant structural bracing versus more conventional part width. Preserving the wearing surface or overlays from chlorides will extend and prevent replacing the structural deck. That's the idea. Question 2, hopefully you did well. What is the purpose of a damper or wind tie? You remember that first video, the Dubrovsky Bridge in Croatia? It's reducing and controlling that stay oscillation. You knew that one. Question 3, one of the biggest challenges to inspecting cable stay bridges is that the primary load carrying wires are covered and protected. True or false? True. Structural health monitoring, careful inspection of preventative items is necessary. Question 4, tie-down systems should be considered secondary members. That is false. I hammered that one pretty hard. Tie downs will prevent uplift. They are designed at the end of the smaller unbalanced spans. And last question, drum roll please. Accessing cable stays, floor systems, and cable stay towers is impossible. False, it is possible. All right, I'll leave my contact information up there. And I'm gonna switch to the chat. See if we have any questions. False. Good job, John. Payman, I'll turn it over to you. And I'm available for question, answer. I don't know if I hit my max.
Yeah, I think if you have the chat function in front of you, I would say that people would post the questions
on. No questions. I must have been just comprehensive.
Covering all aspects. Question.
Mike asked how thick should the overlay driving surface be from your experience? We just follow bridge design manual. It's the new section we incorporated. It's different from microsilica. I want to say, I don't know off the top of my head. I'm going to say 1 1/4 for latex modified, and microsilica is a little thinner. Oh shoot, I'm going to punt to the BDM. Is building cable stay bridges discouraged for their complexity? Absolutely not. No, it's not discouraged, but you do have to weigh the costs. We would build, I mean, we have 9 of them. We built 3 within the last 20 years, 4. And so I think it's the most economical structure to make it over the Ohio River and to make it over the Maumee River on the interstate. There are some, it is a good structure type, and sometimes it's the best structure type for your crossing. And but building an expensive complex structure does come with its challenges. So it's worth weighing the risks, cost, demand, and not just letting the public absolutely decide every time what the bridge should look like. But good question. So how do you budget the repair cost since the bridge repairs are time sensitive? Wow, that's a good, that's another talk, I think, how we budget these things. I don't know if you mean from state DOT perspective. I will say we have a separate pot of money of almost 200 structures meet the requirement for what we consider a state major bridge, and we budget major bridges from central office. That way the district isn't shouldered with their entire budget going to one bridge. For the border bridges, it requires both governors to get along and agree to a price. And generally, we've found the border and made a percentage of, we share the cost with the border structures. Justifying preventative maintenance, now that is a huge issue. Justifying preventative maintenance, let's say we have a bridge that's poor and failing, not failing, but just poor, needs an investment. How do you justify putting money into a good bridge when you have money that needs to go into a poor bridge? That's a really good philosophical question. I'll let somebody else answer that. But I think for cable stay structures, justifying the life cycle cost will answer the question. So we just don't want to be the first state to replace the deck on a cable stay structure. So it's probably a little bit of fear driving that and common sense. Will your presentation be available to attendees afterwards? I don't know. Payman, I guess someone's recording it, and I can make a PDF available, no problem. But how to do that, I think that's going to be, let Payman answer that. Is maintenance cost of cable stay bridge much higher than other types of bridges? Maintaining cable stay structures is much higher. It's a cost of having that nice structure, much higher. Inspection costs are higher. Construction costs, inspection costs, design costs, you know, load rating, everything is bigger and badder with a cable stay structure. Kind of like, you know, is owning a Ferrari, is that, you know, does that cost more than owning I don't know, a Honda Odyssey? But absolutely more expensive. Any reason the Toledo Skyway Bridge was named Veterans Bridge? Most of our bridges are named veteran. We've got a few veterans structures. I don't know the naming. That's usually structures are named with that what's it called, like a colloquial name through state legislature. So state legislature enacts the name through the Ohio Revised Code. I don't know why it was named Veterans Class C Skyway. Back when I was inspecting it, probably 2008, 9, 10, just after it was built, it was called Maumee River Crossing, so the MRC, and it was named Veterans Class C Skyway shortly, you know, 2008-ish. I don't know the process or why it happened, but it's got two names in my head. So I'm guessing Payman will follow up with the presentation if you'd like some of the slides to review.
I think that's what we have. Thank you very much, Mike, for covering this and all the questions. If you do give me the PDF of the slides, I will distribute that to all the attendees.
Okay.
And, tomorrow's seminar will be at 11 o'clock on bridge structural design, process, philosophy, and unique aspects by Dr. Hadid Cezanne, Ohio State University. And if there are no other questions, again, I really appreciate your time and your effort put into this wonderful presentation. Thank you.
Thanks.